We'll complete the discussion of Bernoulli's equation by looking at confined flows, the topic of confined flows, and then some measurement devices like weirs and orifices. And then we'll also discuss the concept of energy grade line and hydraulic grade line. Alright, if we have a confined flow, say in a pipe, and let's say that the pipe is not a uniform cross-section as shown here in this diagram, just conceptually. We've got a section of pipe between point 1 and point 2, and there's a fluid that's moving through that at a discharge, capital Q. Discharge has dimensions of length cubed per time. We can use Bernoulli's equation to determine variables, let's say, or quantities at point 2 if we are given the quantities at point 1. So let's look at Bernoulli's equation for this situation. Let's say that we measure the pressure, the elevation, and the velocity at point 1. We can determine unknowns at point 2 by applying Bernoulli equation and the continuity equation, which we really haven't talked about yet, but we will talk about it now. If we know the pressure, velocity, and elevation at point 1, we can compute the constant that we've referred to. This is sum is equal to C1, the constant at point 1, and that's the same at point 2 along a streamline. And the streamline is passing between these 2 points like that. At point 2, the sum is pressure at point 2, P2 plus gamma 2 times Z2 plus the density at point 2 times the velocity squared over 2. That's the same constant. The sum of those numbers is the same constant. Now if we know the elevation, which we would at point 1 and point 2, then we can determine there's one value that's known on the right hand side of the equation. So this quantity will be known, but what will not necessarily be known would be these 2 quantities here. So we've got one equation, the Bernoulli equation, and we have 2 unknowns. I want to determine P2 and I want to determine V2. And I only have the one equation to do that. It's not possible to be able to determine both with only one relationship. Here we can use the continuity equation to come up with a additional relationship. The continuity equation says that the mass transport or mass movement flow rate at point 1 has to be equal to the flow rate at point 2 in the configuration that we have here. So we might call this m dot, the mass flow rate. And if we have a constant density, we can divide out the density from the equation, and so then the volumetric flow rate, which is capital Q, is just equal to the cross-sectional area multiplied by the velocity at the 2 points. So using that relationship, if I know the velocity at point 1, I can certainly determine the velocity at point 2 if I know the areas A1 and A2. We can just use this relationship here to determine V2. V2 will just be equal to A1 V1 divided by A2. And having V2, I can substitute it in to the Bernoulli equation, and from that then determine what the pressure P2 is. That shows you how you can use both the Bernoulli equation and the continuity equation combined to give you enough information to be able to solve for quantities at a point when you have enough information from another point. Some other characteristics of confined flow are shown here. An important characteristic is the topic of cavitation in pipes and cavitation in other situations. Cavitation is a term that's used to describe the case where the pressure in a fluid drops to the point of the vapor pressure of that fluid. When the pressure in the fluid reaches the vapor pressure, vapor bubbles will form in the fluid, and these then can be created and collapse. And in the situation when it occurs in a container, let's say it might be happening in a pipe, it might be happening in a turbine that's being used, or a pump. When cavitation occurs, the bubbles are created and then collapse, and when these occur near a solid metallic surface, for example, or could be occurring in a concrete surface, the sudden change in pressure and the creation and collapsing of these bubbles wears away, cause wear on the solid surface. And then, of course, this will cause long-term damage to whatever it happens to be. Cavitation will occur in a situation that's shown here. We have what looks like a venturi here, in this case in a pipe, where there's a large decrease in cross-sectional area at some point along the pipe. We know that when the cross-sectional area decreases, the velocity goes up, according to continuity equation. When the velocity goes up, the pressure has to go down. So what's illustrated in the graph below here is that the pressure will, in the pipe to the left between point 1 and point 2, will start to decrease, like what's shown here. And if the cross-sectional area of the pipe gets small enough, then that pressure could actually get to the point where it reaches the vapor pressure. Vapor pressure defined here by P sub V, the vapor pressure of the liquid. And that vapor pressure, or when it reaches that point, you can then have cavitation if it goes below this point. So if we go below that point, if the opening in the pipe gets small enough, velocity gets high enough, the pressure will decrease to the point where you can have cavitation. Now, for water, that occurs if the water pressure drops to about 8/10 of an atmosphere, gets to about 8/10 of an atmosphere negative, and then cavitation will occur. The effect of cavitation is shown here on this propeller in water. Let's say it could be a motorboat propeller, it could be a large shipping propeller, and the cavitation bubbles coming off of that are shown here in the diagram. Those cavitation bubbles can again be created and collapse and can cause wear and tear on the propeller over time, and this damage then has to be repaired at some point, or the propeller has to be replaced. For flow measurement, there are devices such as venturi meters. There are orifices and nozzles that can be used to make measurements of discharge. And what we see here for an orifice as an example is the equation to calculate the discharge is equal to the area of the jet that's passing through the orifice. This is an orifice, it's just a pipe. If you were to look at the pipe along in this direction, what you'd see would be a inner layer. So you've got the pipe here, and then what we would have would be a small opening through which the water is passing at this point right here. So it's an annular ring that would be inside there that would have a small opening, and the cross-sectional area of that opening is equal to A2. A1 is the cross-sectional area of the pipe, and if what we do is we measure with a manometer the pressure at point 1 and the pressure at point 2, we can substitute in this equation if we know the density of the fluid. and we can calculate the discharge. This equation is derived directly from Bernoulli's equation, as what we've done before. Here we'd use Bernoulli's equation and the continuity equation. The continuity equation requiring that A1 V1 be equal to A2 V2. And then of course we just apply Bernoulli's equation as we've seen before between point 1 and point 2. In general, we would need to make some corrections for this, and that because of the fact that things are not perfect, curving streamlines, some of the turbulence that's occurring downstream of the jet leads to some energy losses that are not necessarily accounted for directly with the Bernoulli equation. And so generally what we come up with is we have a discharge coefficient for the orifice, or what we call an orifice coefficient. And so take this equation that we have up here, and we have to correct it for the fact that the flow is not ideal with parallel streamlines and so forth. There is some converging of streamlines, and as you see here, there's some secondary currents that are occurring in the flow, and those secondary currents lead to some energy losses that are not accounted for by Bernoulli's equation. So this coefficient is not determined theoretically. That coefficient is determined by running experiments where you measure the flow through the pipe, you measure the pressure at point 1 and point 2, and from that we can determine what the discharge coefficient needs to be in order to make this equation work. We'll see in an experiment that we'll do in the laboratory the case of a sluice gate, where we've got, you might think of this as being a dam. We back water up behind that dam, and we open up the bottom of the dam. Let's say we raise the gate slightly, so we raise this up, and we make a small gap underneath, and what will happen, of course, is that the flow will go underneath the gate, as shown here. So again, we can apply the same relationship that we used for looking at flow through a jet. The difference here is that you might think of this as being, this is the bottom of the container, so the flow is confined here. You can think of this as being 1/2 of the jet that we were looking at before, because there's no fluid down in here to create the other half of the jet coming out of the opening. We again just apply Bernoulli's equation as we've done before. In this case, the opening is not circular in cross-section, it's rectangular in cross-section. So there is that difference between this and what we were looking at when we were talking about a jet. And the width into the vertical plane, going perpendicular to the vertical plane, the width of that gate is equal to b. So there's a certain width to that. We can calculate the discharge if we know the variables that you see in the diagram here. If we've got the depth Z1 and we've got the depth Z2 and we know the width, we can calculate the discharge coming through that gate. If in the situation where Z1, the depth of flow behind the gate, is much greater than the depth Z2 of the jet coming downstream of the gate, we can drop some of those terms in the equation, and it just simply becomes Z2 times B times the square root of 2G Z1. The equation is simplified. And that looks very similar to the equation we had for a jet, in which case, we assumed that the size of the reservoir feeding the jet was much larger than the opening of the jet itself. Generally, we would, if we know the value of Z2, we can make this calculation. We don't measure Z2 if we just know the opening of the gate itself, that is, the opening here is equal to A. We can make the assumption that the contraction coefficient is equal to 0.61. Remember, the contraction coefficient for a sharp-edged opening was equal to 0.61. So we're making the same assumption here. And we can use that in the case where we actually don't have a measurement of the depth downstream. Let's say if you're designing the gate, you don't have the system to make the measurement. So in this case, you'd be trying to design it, and since we wouldn't know what the value of Z2 is, we could estimate it by just assuming that the Z2 is just equal to A times 0.61. Another device that's very important for measuring flow is a weir, and there are a number of different types of weirs. There's and I've listed those at the bottom of the slide: sharp crested weirs, broad crested weirs, rectangular weirs, V-notch weirs, etc. In this case, we have a rectangular weir of width equal to B. The fluid is backed up behind the weir. You can think of the weir as being a small dam if you want, and the flow goes over the weir as shown. Generally you'll have an airspace. It doesn't always happen, but generally you'll have an airspace which is called the nap downstream of the weir. And what we have is we've got the fluid is accelerating from point 1 to point 2. Now the pressure on these free surfaces here and the pressure on this free surface there would be equal to 0 because that's the atmospheric pressure. But in between those points, the pressure will be non-zero, and you can see this would be an approximate distribution that you could potentially measure in a laboratory experiment. And people actually simulate or calculate these with very complicated numerical models nowadays. The discharge over a weir can be assumed to be very similar to flow discharge through a jet. And so we can make the assumption here that the discharge is just proportional to the square root of 2 times G times the height of the water surface above the crest of the weir. Here's the crest. That height H is the height that the water surface back up here at point 1 is above the elevation of the crest of the weir. So it's a complicated system as far as the flow is concerned. So generally it's assumed that the flow over the weir is very similar to flow through a jet, just like what we've already analyzed. So we can say that it's proportional to the square root of 2gh. We can also say that that discharge is proportional to the height h, which times the value of b, the width of the weir. That h times b would just be the cross-sectional area, proportional to the cross-sectional area of flow of the jet that's coming over the weir. So we can think of that flow over the weir as being a jet. Now we can see here that the cross-sectional area right at the weir is not equal to capital H times B, because this water surface here is lower than the value of H. And that's why we have a coefficient C1 in here. You can think of it as being a contraction coefficient if you wish. That coefficient is multiplied by the cross-sectional area to account for the fact that there's that the flow is not exactly that of a jet. As before, we would use experiments to determine what that contraction coefficient would be. And there have been many experiments done such that if you pick a weir in a design that has a geometry similar to the geometries of weirs that have been tested, you'd be able to pick out what that discharge coefficient is from a table. Alright, in the laboratory too, you're going to be doing measurements in which you'll be able to calculate energy grade line and hydraulic grade line. Alright, so we're going to get the definition here. The energy grade line is an expression of the total hydraulic energy in a system. And here it is, the locus of points for the total energy along a streamline, essentially along a conduit, in other words. So the energy grade line is just the locus of points, and the way in which we're going to express the energy at a given point will be written a little differently, but it's basically the same thing as what we have in the Bernoulli equation. But instead of the pressure P, the elevation, or the gamma Z plus 1/2 rho V squared, what we've done is we divided through by gamma. So here we've got the pressure P sub I divided by gamma plus Z sub I, because we divided by gamma, the gamma ZI goes just to ZI, and then 1/2 rho V squared, or rho VI squared. When we divide that by gamma, it gives us VI squared over 2G. The sum of those three numbers at any given point I along a streamline, so let's say that we just are looking along a streamline S. At any given point I along that streamline, I can, if I have a measure of the values of PI, ZI, and VI, I can calculate the sum of those numbers, of those values, and that will be the energy grade line at point I. And if I were to do that at a bunch of points along this, I would be able to define a line. I would have one value at each one of those points. The locus of those points would be the energy grade line. According to Bernoulli's equation, the sum of those three numbers should not change as we go along a streamline. And theoretically, if we meet all the assumptions of the Bernoulli equation, the energy grade line should be a constant. It should be horizontal. If you were to plot it versus x, for instance, in the horizontal direction. The hydraulic grade line is similar to the energy grade line, but instead of having v squared over 2g in it, it just has these two terms here. And so it's calculated the same way at all the points, and the locus of points defines the hydraulic grade line. So let's look at a situation here in a pipe that's got a slope to it. We measure the static pressure using this tube here, and we measure the dynamic pressure using the pitot tube that's shown there. The difference in the static pressure and the dynamic pressure, or the difference between the fluid levels in those two tubes, gives us the dynamic pressure, and from that we can get, of course, the velocity at point 1. Same thing at point 2. So we measure the static pressure. We know the elevation at point 1 and the elevation at point 2. We have the hydrostatic pressure, or the static pressure, at point 1 and at point 2. So at those points we can define B1 over gamma plus Z1 plus B1 squared over 2G. According to Bernoulli's equation, this should be equal to P2 over gamma plus Z2 plus B2 squared over 2G. Each one of these 2 points are 2 points out of the entire set of locus of points that we could draw. So I could have these measured at a bunch of different points along this pipe, and summing the numbers together, they would all give the same value, because remember, along a streamline, the sum of those numbers will be a constant. So our locus of points creates this energy grade line, which is just a constant elevation or constant value. There's a difference, though, with the hydraulic grade line, because the hydraulic grade line is just the sum of the pressure head, P over gamma, plus elevation head, Z. And we can see that those numbers are not a constant when you sum them together. And so the if we were to take the locus of points at all these points along here, just if you just look at point 1, the hydraulic grade line is at that point, and then you come over here to point 2, hydraulic grade line is at that point, because the pressure is decreasing due to the fact that the pipe is getting smaller in diameter. The velocity is going up, the pressure has to decrease when you go between those 2 points. So the energy grade line in this case is horizontal. Hydraulic grade line is not constant.